record the lesson until now, but that is okay. It's recording now. Okay, yeah. So the first equation about pH and pK is pH is negative log 10 of hydronium ion concentration. Good. With only on to you, what's another pH formula you know?
pOH is negative log of hydroxide ion.
Good. And Sid, what does a high pOH tell you? Is it an acid or a base with a high pOH?
It tells you it's a acid.
Good, right? And the formula Ethan might have thought, Sid might have thought about is pH plus pOH gives you, Ethan, what number does pH, cut off. Nathania, what does pH plus pOH equal to?
14.
Good, right? And what temperature is that dependent on?
Is it room temperature, 25 degrees?
Good, good. Room temperature pressure. Okay, now we can talk about the more complex formulae. Now, I didn't explain these ones, which is hydrogen ion concentration is 10 to the power of negative pH, hydroxide is 10 to the power of negative pOH, but I'm assuming if you know 2 unit, you should know basic log transfiguration for that formulae. But coming down to the rest of the equations, Rithania, what other formulae do you know? Rithania, any other formula? Could be pKa, K formula as well. Quickly.
Was it pKa plus pKb is equal to 14?
Yeah. All right. We'll start with the simpler ones. pK terms of Ka, right? The pKa is negative log 10. Ka, pKb is negative log 10 Kb, right? So Ethan, coming to you, a strong acid, what would its Ka value be, high or low?
Wait, a strong acid?
Yeah. High or low Ka?
Strong acid should have a high Ka value.
Good. And what should the pKa be?
pKa low.
Remember,
pKa
it's
should be
inverse when you negative log,
yes,
so
low. Ka is high, so pKa should be low, right?
good, right? It's the exact opposite for a weak acid. Same thing with a strong base. I'm not going to repeat that, but in terms of pKb, now, good job. Bethany, you mentioned pK plus pKb. But I'll start with the Ka times Kb. So Ka times Kb, Sid, what does that equal to?
Kw, so 1 times 10 to the power of negative 14.
Good. And what temperature again is that based on?
25 degrees.
Good. And actually, that pK plus pKb, what does that equal to?
pKw.
Which is?
1 times, oh no, 14, is it?
Good. Just 14. Right? You can log this, you can negative log this equation and get to this equation. So you can derive them all. Very good. Now there's one equation I haven't mentioned here. And Sid, do you know what that equation is by any chance?
Does it have to do with Kw?
No.
I don't know then.
Who's heard of the Henderson-Hasselbalch equation? Anyone? Okay. Well, this equation is solely to do with buffers, right? We're going to talk about buffers very briefly before I explain it. Now, the hard part about this equation, the equation and remembering it, batteries. Just quickly charge my iPad. Okay, good. As I was saying, the equation is actually not too bad to remember, and it might be in the back of your data sheet, double check, but it's pH, I actually don't think it is, but it's pH equals pKa plus log 10, the degree of ionization of an acid, right? But when you're looking at how much of an acid ionizes, if you have HA, gives you H plus A minus, and 70% of HA becomes A minus, the degree of ionization is 70%, right? So to calculate degree of ionization, you just divide A minus by HA. And this is the Henderson-Hasselbalch equation. pH is equal to pKa plus log 10 A minus on HA. Now, the hard part of this question is knowing when to use it. And let me show you how to pick that up, right? So we need to first understand what a buffer is. Now, when you're playing a video and there's buffering, the video is stopping or resisting being played. Very similarly, a buffer in chemistry and the pH buffer is a solution that is resisting changes in pH. Now, the way you can have a solution that resists changes in pH is by having a weak acid and its conjugate base. So, Rathania, pick a weak acid for me. This is a weak acid you know.
Acetate.
Is acetate a weak acid?
Acetic acid, sorry.
Good, right? So the acid is CH3 COOH plus H2O. Gives you the hydronium ion. It gives you CH3 COO minus, right? Acid, conjugate base. Okay. Now, if I add an external acid to this solution here, right? If I add a solution that increases the hydronium ion concentration, okay, it's an acid. By whose principle will the system respond by, and what will happen?
So the Shadowley's principle.
Yeah, and what will happen to the equilibrium?
Okay, so the addition of H3 plus 3O plus ions will cause it to decrease, so that the reverse reaction will be favored to decrease the H3O plus.
Good. The only careful thing is the addition of H3O plus ions would cause it to decrease doesn't make sense in terms of your wording, but I know what you're talking about, right? So to word it to all of us, when you add an acid and it externally contributes hydronium ions, you're disrupting this chemical equilibrium. The equilibrium will then respond by favoring the reverse reaction, so shifting this way, in an attempt to partially decrease hydronium ion concentration. So you need to use the word partial, right? Well, there's still a net increase. That's why I'm showing you. You've gone up by this much, you've come down by this much. The net change is still up by that small magnitude, right? So the pH will still drop down. What will happen is the reverse reaction will be favored, and that's an attempt to resist the decrease in pH caused by the addition of hydronium ions. So essentially, buffers are just any solution or any acid-base solution which forms an equilibrium, because then it's going to obey LCP and it's going to resist changes in hydronium ions being added. Now, this is how you remember it. If you ever see a weak acid or a weak conjugate base, you should also think of Henderson-Hasselbalch equation. This is an equation that's almost exclusively used for buffer questions. And on that note, first question is question 5. I'm going to give you all about 3 minutes to do this question. Okay? Good. All right, I'm going to get some water. I'll be right back. But hit the raise hand icon once you've got an answer. Who's got an answer? Sid?
I'm still working through it.
Okay. Akshita?
Yeah, still.
Okay, maybe get us started on this, Akshita. So what's the first step? All right, Ethan, what's the first step with every single calculation question you do?
Writing equation for it.
Good. So what is the equation?
It is. I'm not 100% sure if it's correct or not, but it's C6H5COOH. That's the acid.
Good, but let's say you don't know the acid. So I should have helped you guys out here. Benzoic acid is a monoprotic acid. Okay. They usually would have given you that in an exam question. Okay, you aren't meant to know what benzoic acid is. Good. It's good that you know what the benzoate ion itself is, but let's just say it's HA. All right, but yeah, keep going. HA, what would the equation be?
Is it a single arrow and then the sodium benzonic plus H2O? Am I right?
It wouldn't be sodium benzoate plus H2O, sodium benzoate plus H2O. This wouldn't be the equation. And the logic for that, Ethan, is first of all, whenever you have a metal ion in acid-base chemistry, Control Alt Delete should not be there. Does not contribute to any acid-base reaction. It is simply an ion that is hanging on to another ion. So first step is always take the metal ion out.
Yeah, all right.
Right? Now the next step is this doesn't make sense by the law of conservation of mass because you have a random oxygen coming out of nowhere. So this would have been a more appropriate equation, but this is not a Bronsted-Lowry equation. Ethan, whose equation is this? What scientist made this equation?
Can't remember, sorry.
Ruthania, who's the scientist that made this equation?
Is it the Henderson?
Someone, come on.
Arrhenius.
Good, right? You can't be forgetting this stuff, guys. It's basic, it's just history. Arrhenius, all your acid-base knowledge until today, and then proton transfer reactions, Bronsted-Lowry, right? I don't care if you forget Humphrey Davies. They're good to know, but the high yield stuff, you can't forget that, okay? All right. Let's make sure we're revising more often, because if you did not know that, you straight away aren't at a band 6 level right now, right? You're sitting in terms of you need to first improve the content there. So HA plus H2O gives you, now, benzoic acid is not a strong acid. Hopefully you all know that because you know all the strong acids. Sulfuric acid, hydrochloric acid, nitric acid, hydrobromic acid, hydroiodic acid. Those are your strong acids. Everything outside of that is weak. And so when you saw benzoic acid and you had to pick, it would be double directional arrows. And so now you're left with A minus and H3O plus. This is the equation I wanted you all to write. Okay, so good. Do you see, sometimes it's hard to write the equation. This was a hard one to know the equation for, but hopefully all of you could work it out in the end based on coaching it. Britannia, next. What's the next step in every calculation question?
Writing down the values.
Good. So very quickly, tell me, what are the values we have?
We have the moles of benzoic acid, which is 0.2.
Good. So I want you to say N of HA 0.2. Keep going.
And then N of A minus is 0.1.
Good. Benzoate is A minus science. N of A minus is equal to 0.1. Very good. Keep going.
The volume of water, V of H2O, is 54.9 times 10 to the power negative 3.
Good. So you put it here. V of H2O So 54.9 times 10 to the power negative 3. Good job. Keep going.
And Ka of HA is 6.3 times 10 to the power negative 5.
Good. Now, what are they asking us to find? It's always good to write the question as a data point. So what are they asking us to find?
pH of
Just pH of the equation, right? You can't say pH of something. It's just pH of the solution. Because what is pH? It's hydrogen ion concentration, right? So pH is question mark. Good. Sid, what do I do now? And what equations are you thinking of at this point?
I'm thinking of since we have Ka and we have the concentrations of A minus and HA, we could use the Henderson-Hasselbalch equation.
Good. Right. Now, again, did you realize you guys all knew to use that equation because I just explained it to you, right? But think about it. After going through 4 modules of HSC Chemistry, if this question came up, I think 90% of students would just try working with Ka and do a Rice table or finding pKa or trying to use pH as negative log 10 hydrogen, and the Henderson-Hasselbalch equation completely slips their mind. So what you all need to work on is, when do I use a Henderson-Hasselbalch equation? And I want you to remember this. Ever see a question with Ka and equilibria and it's asking for pH? Right, so equilibria, Ka, and it's asking for pH. It is begging you to use a Henderson-Hasselbalch equation. Okay, that is for the vast majority of questions. All my batteries going down. One moment, just plug my laptop and iPad into. Very good. So that's it, right? So use a Henderson-Hasselbalch equation. Before that, write down the Henderson-Hasselbalch equation. pH is equal to pKa plus log 10 concentration of A minus divided by the concentration of HA. So let's find pK. Ethan, what's the formula for pK?
pK formula is negative log 10 of Ka.
Good.
So that's negative log 10 of 6.3 times 10 to the power of negative 5.
Good. Have you got an answer for that?
Not yet.
All right, that's all right. Ruthania, while Ethan's solving that, can you tell me what else can I find?
Sorry, what were you asking?
What else can we find? And I've written it already. So tell me, what's the concentration of HA? Akshita, what's the concentration of A minus? Can you guys get your answers? Shout it out.
pKa is 4.20.
Good. 4.20. We're going to store that as A. Good. Next, Ruthania, Akshita, what do we get?
For the concentration, it was 0.001.
Concentration of?
A minus, was it?
0.0. Are you sure? 0.001. We're dividing 0.1 by 54.9.
Oh, sorry, wait. 182.14, sorry.
182.14. Good.
Yeah.
Okay. Wait. 0.1 divided by 54.9 times 10 to the power negative 3. You got 182.14. I'm just thinking,
Yep.
182 moles per liter sounds like a crazy amount. I've never seen that ever in real life. And 0.1 divided by 54.9 times 10 to the power negative 3. Oh, it might be. Yeah, did everyone else get the same value? Might, given the volume.
Oh, wait. On the question it says isn't it to the power of negative 5?
Why is it to the power of negative 5? That's Ka. This is Ka. Did you sub that in as volume?
No, you know wait, I thought the H2O, the power was 5, but it's 3.
Okay. Yeah. All right. But yeah, let me know what you get. Rithania, what did you get?
I got 3.642.
Good. That looks good. Stored as B. And Akshita, what did you get for concentration of A minus?
Sorry, it was 1.8214.
Good.
9.
Stored as C. So then pH is equal to pK, which is A, plus log 10 of A minus, which we put as C, and we're going to divide that by HA, which we said was B. So what's pH equal to? Sid, your turn. What's the answer?
I got a pH of 3.89.
How many sig figs should the final question be, or decimal points?
2, so it'd just be 3.9.
Yeah.
I have a,
it can be to 2 decimal places, because your answer in pH is usually should be to the lowest number of decimal places that is the lowest sig figs of the question. So looking here, there's 0.2 is 1 sig fig, so it should be to 1 decimal place. So you're right, it should just be 3.9. So you can write equals to 3.89 and then round it up to 3.9, 1 decimal place, given 1 sig fig here, right? So answer in pH is usually lowest decimal places that's equal to the lowest sig figs in the question. Question set?
with pH. So say like you have a pH of like 11 point something something, and they ask you two significant figures. Do you only consider the decimal like that comes after the integer, or?
Yeah. So if it's 11.851 and the question, the lowest sig fig in the question is 2, your answer would be 11.85 because you're doing it to the number of decimal places. That is the lowest number of sig figs of the question. So if the question, the lowest number is 2 sig figs, your answer will be to 2 decimal places. Does that make sense?
Yeah, thanks.
Good. And usually it's not going to be anything crazy. You're never going to get a HC. They always think about this stuff. So they're never going to give you a HC question where the answer is, 11.91654, and you have to round it to, 1 sig fig. That doesn't make sense. They say round it to 10. That doesn't make any sense. They'll always use appropriate sig figs and decimal places, so you round it off fine. Just keep that. PhD, Okay, you guys are starting to get it, but let me just ask you this. Is this a Henderson-Hasselbalch equation? Or will I have to use it to solve this question? Yes or no? Hit the raise hand icon when you get an answer. Don't say it out loud so everyone else can either pick it up or exclude it. Like I said, knowing to use it is the hardest part of this question. All of you will know it. There's always some students who forget even after they know. But Ethan's got an answer. Oh, sorry, the screen. A low battery. If I don't touch the screen, it stops sharing. So I apologize. Let me put it up for you again. Okay. So Ethan's got an answer. Who else has an answer? Hit the raise hand icon once you get an answer.
Do you mean the answer of like using the Henderson equation or not, or like the acrons
Yes.
of the?
I don't want to know the actual answer. Just do I need to use
All
Henderson back or not? That's what I want to know. So okay. Actually, do I have to use the Henderson-Hasselbalch equation or not?
I think yes,
Why?
because there is reverse reaction. I mean, it's asking for pH 1.
Good.
It's asking for the KB, like it has KB in it.
Good. So K, KB. Good.
Yeah.
What else?
And reverse reaction.
Yeah, good. That's it. That's the little triad, right? In fact, even if you get that triad, if you're ever asked for pH and the question is hard, think Henderson-Hasselbalch. That's my other tip. If you're ever asked for pH, one of the ways to find pH is Henderson-Hasselbalch, and consider that if no other question or formula works. You can do either of those two things. Never miss Henderson-Hasselbalch in trials. Okay? Does anyone have a question, or is the hands raised just because what I said?
Isn't this equation a straight arrow because it has hydrogen chloride?
It doesn't have hydrogen chloride, it has ammonium chloride, which is
But like,
different.
isn't that the result of ammonia and hydrogen chloride reacting?
Okay, you're thinking, Sid, about the gaseous ammonia dilemma, which is NH3 gas plus HCl gas gives you NH4Cl. This is a gas-only equation. They've told you solution. So you straight away have to think NH4Cl aqueous, right? And you should know all group 1 metals and ammonium salts are aqueous or soluble. As this chloride ion disappears. So the equation is just NH3, that should be NH4 plus water gives you NH3 plus H3O. That'd be the equation, not this. There's no mention of HCl here. Makes sense?
Yep.
Good question. All right. You can do those questions in your spare time. There's a ton of questions here. But we'll talk about strength of acid and bases shortly too. I want to give you guys an exam question. Done a lot of good question. All right. Question 27. It's 2 marks. I'm going to give you all about 3 minutes. After we do this question, we'll start going through acid-base strength, and we'll also start doing titration. Okay, good. Be right back. Sorry guys, let me reshare. Stop sharing the screen. Okay. All right. Did get us started on this question.
So first, I write the equation Mg OH2 equilibrium with Mg2 plus and 2OH minus.
Good.
And then I wrote the equilibrium expression.
What is, yep.
So, Mg2.
Yep.
Okay,
Keep going.
yeah.
Keep going. Yeah, don't worry about what I wrote. Just do it your way.
And OH minus squared. And then I let the concentration of OH equal to S.
Okay. So did you do S times S squared?
Yep.
Is it S times S squared?
It'd be so S times 2S squared.
Good. So you didn't let OH equal to S, you let Mg equal to S. Is that what you said? Or?
Yeah, okay.
Yeah,
I think that's what I meant.
Yeah. So you can say let the concentration of Mg ions, Mg2 ions, but keep losing charge. Good. But yeah, let the concentration of Mg2 plus ions equal to S, right? And if this is equal to S, there's a 2 in front of this, so this is 2 times S in terms of its concentration. So when we sub that in, KSP is equal to S times the concentration of hydroxide, which is 2S now, squared. Good. And what is a KSP equation? What is a KSP of Mg or H? How did you find that, Sid?
So S equals to 9.2, 9.24.
Was it? S equals to 9.24? Where did you get S equals? So the magnesium hydroxide, the mass concentration that can dissolve in is 9.25 grams per 100 ml. But it's not the concentration in moles per liter. Does that make sense? When you sub in the S value, that has to be in moles per liter. Are you with me?
Yep.
So Akshita, how can we find the concentration of magnesium hydroxide in moles per liter? Akshita, how would I find the concentration of magnesium hydroxide in moles per liter?
Put that over. Oh no, first convert it into moles, which is moles times mm.
Good. So therefore we can say in 100 ml, the maximum mass of magnesium hydroxide, or the mass of magnesium hydroxide, is equal to 9.24 times 10 to the power negative 4 grams. So the number of moles of magnesium hydroxide must be equal to mass divided by molar mass. Ritanya, tell us what that is. While Ritanya is doing that, let's say we stored that as A. Ethan, I've got the number of moles of magnesium hydroxide in 100 ml. Can I find concentration?
Wait, sorry.
I've got the number of moles of magnesium hydroxide in 100 ml. Can I find concentration?
Yeah, you can.
Good. So what's the formula for concentration?
Concentration is number of moles divided by volume. So volume is 0.1.
Good. Good. So Ritanya, what did you get for A? Ritanya? What's your answer for A?
It's 1.5 times 10 to the power of negative 5.
Okay, good. So then A divided by 0.1, whatever that is, it's stored as B.
I got
Okay,
Sorry,
Yeah.
I got 10 to the power of -4 because it's 100 per 100 milliliters. So like
Yeah.
you
Oh, as in for B concentration.
no, because oh, okay, yeah, I see you did the thing after.
Yeah, the divided by 0.1. Yes, that B is 1.5 times 10 to the power -4. Okay, good. So you got the concentration of magnesium hydroxide. What's the concentration of magnesium? Sid, is it equal to the concentration of magnesium hydroxide 2 times, what is it?
Yep, it's equal.
Good. So then we can sub that straight in, right? You can say that's B. So you can say, therefore, KSB equal to, do we need to find KSB? That's the question.
No.
Okay. Yeah. If you think about this, guys, KSB, when you sub this in, you're going to get KSB is equal to B times 2B squared, which is great, and you'll find KSP. But the question didn't ask you to find KSP. It asked you to find hydroxide ion concentration and POH. So now all you need to know is then what's the concentration of hydroxide ions? What does that equal to? It's 2S. We said S is equal to B, which is 1.5 times 10 to the power -4. Concentration of hydroxide is 2 times 0.5 times 10 to the power -4. Or 3 times 10 to the power -4. Can we find POH, Ethan? And what is your answer?
Wait, I'm not up to that yet. Sorry.
It's all right.
Sure.
Nathaniel? Nathaniel, what's your answer for POH? And what are you going to sub in to get POH?
It's negative log 10 of OH.
Which is? Three times 10 to the power -4. Is everyone with me? The concentration of magnesium is concentration of magnesium is the exact same as the concentration of magnesium hydroxide because there's one block of magnesium in magnesium hydroxide. There's 2 blocks of hydroxide, OH2, in 1 unit of magnesium hydroxide. The concentration of hydroxide is 2 times the concentration of magnesium hydroxide. Ethan, does that make sense? Or do you want me to clarify?
Yeah, got it. I got it.
Good, right? So just times it by 2. That's how we got this. And you're just negative log 10ing that value. So yeah, good. Sid, what's POH equal to?
POH I got 3.499.
Good. Does that qualitatively make sense to you, Sid, for a base to have a low POH?
Yes.
Good. So then you know you're probably right. Okay. Good job. Good. Let's maybe do one more titration stuff. All the way. Okay. Question 22. Give you all about a minute to do A, then a little bit longer to do B. Or ask you to do B. A.
Wait, sorry, sir. I'm not quite sure what you mean by acidic salt and basic salt. And
You might not have been there that lesson. It's all about conjugate acid-base pairs. Did you watch the previous lesson recordings, Ethan?
yeah, not the week before.
Yeah, I think that's when we went through acidic basic salts. Okay, I'll teach it to us again.
Yeah.
But yeah, watch the lesson before last week for it. In the meantime, okay, we might just start going through it now then. Rithania, pick an acidic salt. Or tell me what you've cancelled out, just how have you started to think about this? Or tell me a neutral salt, or give me a basic salt.
CaCl2.
CaCl2. Is CaCl2 acidic or basic or neutral?
Is it neutral?
Good, right? The way I break it down, right, is you look at the salt. First step you do is break it into its ions. If it's a metal ion, like I said, we do not care about metal ions in acid-base chemistry. So then we find the chloride ion. Ethan, what is the conjugate acid of the chloride ion? What is the conjugate of the chloride ion?
Not sure.
So to find conjugates, Ethan, if just add a hydrogen if it doesn't have a hydrogen. If it has a hydrogen, take it off. So does it have a hydrogen?
No, so just add one. HCl.
Good.
2.
Is HCl a strong or a weak acid, Ethan?
Strong acid.
Good. Now you'll need to know this. It's kind of like a chart, but a strong acid ionizes to completion. So it ionizes completely, pretty much. So its conjugate is just whatever's left in this progress bar, which is very little. Do you see that little bump there? So this analogy is to show you the conjugate of a strong is very weak or neutral. So we just said it's a conjugate of HCl, which is strong. So what is the strength of the chloride ion as a base, Ethan? Strong or very weak?
Weak.
Very weak. You guys can't miss this, right? Weak and very weak are very different, so do not mix them together. So Ethan, again, the conjugate of the strong acid HCl, what is it? Very weak or neutral. That's what you've got to say. Good. And so since it's very weak or neutral, it's not going to ionize enough as a base to cause a basic change in solution. So Tania's right. CaCl2 is a neutral salt. Sid, pick a basic salt.
Lithium acetate.
Good. Right. And Sid knows we're going to cancel out the lithium. We've got the acetate ion. It doesn't have a H at the end. Remember, this H does not come off. That's not acidic, basic. It doesn't donate protons. The hydrogen is fixed. We're going to add a H. H3COH. This is a weak acid. Now, again, using this progress bar, a weak acid only ionizes partly. Weak. There's still 50% of our progress bar left. The conjugate of a weak is weak. So what is the strength of the acetate ion here, Akshita? Akshita, what's the concentration? Yeah, good. So I shouldn't say concentration, what's the strength, but very good. So this is a weak acid. The conjugate is a weak base. Right, so good. So lithium acetate. Good. Going back to Ruthania, pick an acidic salt, Ruthania.
MgNO3.
Okay, Ruthania, break it down for me. What are the steps in determining? I don't think that's acidic. I'll show you why, but you can explain it to yourself pretty much. What do we do to determine the pH of a salt, Ruthania? What are the steps?
Does it break it down to anion, cation?
Good. Do we care about the cation in this case?
No.
No. Okay, so let's move on to the anion. We don't care about the cation because it's a metal ion. What about the anion? What's the conjugate of this anion?
HNO3.
Good. Is that a strong or a weak acid?
Strong.
Good. Ethan, what's the conjugate of a strong acid?
A weak base. Oh wait. Is it? Strong acid. Yeah, strong acid. Very weak.
Remember, you can't forget again, okay? Very important. The conjugate of a strong acid is very weak or neutral, right? So Ethan, when you watch the lesson before last week, it'll make a lot more sense. And I explain why that is the case. But for now, in the interest of time, we're going to have to keep going. So the conjugate of nitric acid is strong. So the conjugate of that, nitric acid is strong, so the conjugate of that is very weak or neutral. So Rithanya, is this acidic, basic, or neutral? MgNO3.
Neutral.
Good. Then what is acidic, Sid? There's a couple of salts here that are acidic. Do you know which ones are acidic?
My best guess, well, not guess, but the only one I can see is ammonium chloride.
Good. Good. And actually, I'd agree with you. Everything else is not acidic. They are all neutral. Sodium carbonate is slightly basic. Talk about that after. Potassium fluoride is a little bit of a harder one, but we'll talk about that one later. They'll never give it to you directly by itself as an example. But this is a weak acid. Good. And that's because when you break it up, the chloride ion, the conjugate of chloride, NH4Cl, is HCl. Strong acid, very weak base. Cross that out. Ammonium already has a hydrogen. So we're going to take a hydrogen off. We always take a hydrogen off the cation. We add a hydrogen to the anion to find the conjugate. We take a hydrogen off. Its conjugate is ammonia. Ammonia is a weak base. So Ethan, what's a conjugate of a weak base?
Very strong.
Ooh.
All right.
Remember, weak has weak conjugate. Strong has a very weak conjugate. That's the rule. Weak gives you weak. Strong gives you the exact opposite end of the spectrum, which is very weak. Does that make sense? So again, what is a conjugate of the weak base ammonia?
Also weak.
Good. A weak acid. Very good. So we've got a weak acid cation and a very weak base or a neutral anion. So it's going to overall be a weak acid. Do you see how we're using conjugate acid base pairs to determine the pH of salts? So that's your answer for 22. Good. Not too bad of a question. Here's a decent one. Question 19. I'm going to give you all about a minute. And we'll let you go. Okay, how do we go? So let's start with Akshita. Start us off with this question. Acid HA has an acid dissociation constant, Ka. So what's the expression for Ka, Akshita?
Ka is equal to A over H, A times H over HA.
Okay, we'll start with the equation. HO plus H2O gives you A minus plus H3O plus, right? So what is the Ka expression one more time?
A
Yeah,
times by hydrogen and
hydronium. This is a
hydronium, yeah, hydronium over HA.
Okay, good. And how can you simplify this?
The A, you can get rid of the A, is it?
Remember maths, you can't just get rid of the variable if you don't
Yeah.
like it. This is equal to the hydronium ion. These are equal. They have a 1 in front of both of them, right?
Yeah.
So they're equal. So you can just say this is hydronium squared. We're not going to write that now because you realize if you try that way, this question becomes actually a bit harder. But that's just another way or an expression you can write. Okay. Now here they've asked you, what is the expression for the equilibrium constant for the reaction below in terms of Ka? So let's find, what is the equation here? This is a Kb equation. Do we all realize that? This is a conjugate base combining with water. This is the acid combining with water. Okay, so what's Kb equal to? Sid? What's the expression?
So HA times OH minus over A minus.
Good. Very good. Now, how can we get Kb in terms of Ka? Sid?
KB equals to KW over KA.
Good. So you might remember Ka times Kb equals Kw. If you remember this equation, this becomes so easy, this question, because you can go, all right, well, they're asking for what the Kb expression is. Kb is just Kw divided by Ka, right? But if you forgot that completely, what you can do is go, okay, well, Ka has an A minus on the top. There's an A minus on the bottom here. So what if I swap, what if I find 1 on Ka? What is that equal to? Because I'm trying to make Ka look like Kb, right? So then I'll do Ha divided by A minus times H3O plus, right? And then you have to think, well, what do I need to add to that to change it? And you realize, well, what is the Kw equation? Kw is, or water forms the hydronium ion times the hydrox plus the hydroxide ion. So Kw is hydronium ion concentration times hydroxide ion concentration. Okay, so if I multiply this by Kw, I'll get times hydroxide times hydronium. I can cancel these two out, and that will leave me this equation here. The Kw times 1 on Ka is Kb, or Kb is Kw on Ka. Good. Very good. All right, what we'll do is we'll take a little break. We'll take a 5-minute break before we continue our acid-base strengths, and then we will soon touch upon this, not too important, but titration. Okay, so the next hour we'll go through acid-base strength and we'll touch upon titration. Actually, I thought you had a question.
Yeah, since we're on our break, when are we gonna get our booklets?
Yeah, so they've already been posted to you, so it should be a matter of time. Sometime this week you should get it. Okay?
All right, thank you.
Good. All right, I'll see you guys at about 5:10. Okay, stretch, get some water, get some sunlight if you can. Okay, can you hit the raise hand icons when you're back? Good. Good. All right, let me share my screen. Let's jump up into it. Okay, so coming down here about strength of acids and bases, let's start with Ethan. Ethan, what determines the strength of an acid or a base?
Wait, sorry, can you repeat your question again?
Yeah, sorry, I'm just trying to change the screen. Yeah, there you go. That's a bit better. Okay, yeah. Ethan, what determines the strength of an acid or a base?
Strong acid, they will have the like if it's in a diagram, the proton and the negative ions won't be sticking together, but if it's in a weak acid, the proton and the negative ions will be sticking together, like
Good.
kind of sticking together.
Good. So in terms of exam wording, what I want you to say is degree of ionization. Because when you ionize, that's when the proton and the negative ions separate, as you said, right? So a strong acid is one where the degree of ionization is 100%. A weak acid is one where the degree of ionization is less than 100%. Rithanya, what determines a concentrated and a dilute acid or a base?
If it goes to completion or not, so it would be the equilibrium error.
Concentrated or dilute acid and base is to do with equilibrium. Let me show you there should be an image here that I have. Rithanya, what is this? Is this a strong or a weak acid? Rithanya, strong or weak acid? Why? Akshita, is this a strong or a weak acid?
Strong.
Good, right? It's strong because it ionized to 100%. Not a single proton is joined to the anion. Good. Is it concentrated or dilute, Akshita?
Concentrated.
Good. Why is that?
Because there's a lot of moles.
Good. There's
Like,
a lot of moles in a volume. That's exactly what concentration is. Good. Next diagram, Ethan. Concentrated, oh, sorry. Yes, concentrated or dilute?
Dilute.
Good. Strong or weak?
Strong, because there's
Good.
no unionized molecules.
Good. Sid, your turn. Tell me about the concentration. Tell me about the strength.
So it's very concentrated because of a lot of molecules in the same unit volume, but it's weak.
Very good.
Acid.
Good. Right, because degree of ionization is less than 100%. And finally, Rithanya, back to you.
Would be weak.
Good. Why?
Because it's ionized.
Good. And concentration?
Would be dilute.
Good. Why? Because there's not many moles in a volume, right? Just apply the C equals NV formula and that would make sense. Does that make sense? Good. All right. Okay, let me give you a calculation question before we finally touch upon our titration questions. Oh, these questions are something. I'll give you this question. Question 2. I'll give you all about 4 minutes to get started. So this is just to see whether you're good at. So as you might know, all the pH, pKa calculation questions we've done, a lot of them actually didn't involve a direct acid-base reaction. A lot of it was an acid or a base dissolving in water. This is an actual acid-base reaction. So give this a go. It's a slightly different kind of question, and you'll see how. Hit the raise hand icon once you get an answer. Good. How do we go? Who's got an answer? Let's start with with Tanya. First step with these questions.
Equation.
Good. So what's your equation?
I did HCl plus. That's the thing. I don't know what it's adding.
Yeah, in the first step, we're not adding anything, but in the second step, we are. Right? What are we adding in the second step? So the first step is a dilution. It's not a reaction. You agree? This one right here. But what happens in the second step?
The diluted is being added to sodium hydroxide.
Good. So there is a reaction between HCl. It doesn't matter if it's diluted or not. It's still HCl. It's being combined with sodium hydroxide. Good. So then what's the final product? HCl plus NaOH, I'm sure we all know, is NaCl plus H2O. Right? So let's start writing our data. So Sid, what are you going to write as your data?
So I did C1 V1
Good.
equals C2
Yeah.
V2.
But before you do your formula, it's good to label it. So yeah, C1 of HCl, so this is a pre-dilution concentration of HCl. What does that equal to?
0.11 and
Good. And V1?
and 0.0267 liters of
Yep.
that.
Good. And then what other data do we have?
We have V2, which is 83.9 plus 26.7.
Good. Right. So the first way I tried to trick you all is by saying by adding 83 ml. So V2 is not 83 ml, and they'll often trick you or try to trick students this way. You know, if you have 10 ml that added 90, V2 is not 90, V2 is 100. So good pickup. So what is that, Sid? So you said it's 83 plus 26. Just tell me what the amount is.
110.6 ml.
Good. You got V2. Good. Keep going.
And then you sub it into C1 V1 equals
Remember,
C2.
before that, write all your data. And then
Okay.
you can
Okay. Then C1 NaOH is 0.011.
0.011. Good.
And V1 is 0.0937 liters.
Good. 0.0937 liters. Good.
And I don't know where to put the last bit of information.
Yeah, so maybe you can just write under here and put a line before we go through the plus 100 ml of solution. Okay, very good. So now, stepwise, let's apply C1 V1 equals C2 V2. So that is in another color. So this is my calculation step. I think with any dilution question, it's always important to do one extra thing. Actually, though, what's the one extra thing you want to do so you don't make silly mistakes? Actually, though, what's one other additional thing? We've done equation, we've put in our data. What's one safe
Diagram?
Yes, very good, right? So you can go, all right, we had 26 ml of HCl, and then we can do it like this. There's a beaker, there's 26 ml of HCl, 26.7 ml, and we added 83 ml HCl. And then that's then combined with sodium hydroxide of 93 ml. And then we further add 100 ml at the very end, plus 100 ml. Okay, good. So let's apply the C1V1, C2V2 formula first. The C1V1 equals C2V2. What are you trying to find, Sid, first?
V2. Oh, sorry, C2.
Good. We have V2. Good. The C2 of HCl. So C2 of HCl is equal to C1V1 over V2. And that's going to be equal to, what do we get as our answer? So Tanya, what did you get as C2? still solving it. That's all right. Akshita, has anyone already got C2?
I got 0.0265 moles per liter.
Good. All right. So that's a concentration C2 of HCl. Okay, keep going, Akshita. So we've got C2 of HCl. What can we do next? Come on, Akshita, what else can we do? What kind of question is it now where you've been given data about both reagents, HCl and NaOH?
Limiting reagent.
Good, right? We don't care about C1 anymore. We've used that. We don't care about V1 anymore. The V of HCl is this amount now. The C of HCl is this amount now. You've got C and V of both of your reagents, Akshita. What can we find?
Moles.
Good. If you have C and V, you can find N. So what's the number of moles of HCl? Using V2 and C2. What's the number of moles of NaOH? We get. Okay. So no one's got an answer yet, is that right?
For this question, don't you only need to find NaOH since HCl NaOH is the limiting reagent?
Well, we need to know by finding number of moles. If I haven't found number of moles, I don't know who the limiting reagent is, right? Because, yeah, so once I find this and then I find who the limiting reagent is, then I can go down one path. But right now, I still need to know who the limiting reagent is. When we use this, so what do you get for number of moles of HCl and number of moles of NaOH? Come on, guys, what do we get? So, has anyone got an answer yet?
I got the one for HCl.
Good. Ethan, give it to me.
0.24.
Good. 0.24 moles. Yep. And what do you have for NaOH? Someone has to.
Still working on it.
Yep. Good. Do you guys need one more minute? Only because this is one of the question types you've done quite often. I don't want to spoon feed you guys through this question. I wanted someone to have a final answer already. What was the challenging part until now? Sid, for you, what was the challenging part that stopped you from getting an answer? Or was it just time?
Time. And I kind of assumed
One limiting reagent?
yeah, from the concentration.
Okay. But always just wait till you have the number of moles of each to compare equally. But okay, sure. Maybe I'll give you guys about 40 more seconds or so. I want a final answer, and then we can confirm the way to solve it. Because at this point, you guys should be pretty good with these limiting excess reagent questions. Hopefully you all have some snacks while having class after the second hour. I get very hungry after a couple of hours. I might get some chocolate and watermelon. Be right back. Sorry, the screen has stopped showing. Reshare it again. Okay.
So yeah, so I got a pH of 2.99.
.99. So what was your approach from here? What did you get in all your numbers?
All right, so for NaOH, I got 0.00103.
What's the NaOH is your limiting reagent, so HCl is the excess.
Yep.
What are you going to find next?
So then you've found the moles of water.
Why did you find the moles of water?
To find the H3O plus concentration.
You found the number of moles of this substance? Is that what you did?
Which substance are you talking about?
This water? Is that what you said you found?
Yeah.
That doesn't make much sense to me in terms of working out. What I would have done, HCl is the excess, right? So I want to find out how much HCl is remaining after the neutralization reaction. So what I would do is I'd go, well, number of moles of HCl that's remaining is equal to the number of moles of HCl that's in total minus the number of moles of HCl that reacted, right? And to find the number of moles of HCl that reacted, it's a 1-to-1 ratio. It's going to be equal to the number of moles of your limiting reagent. Remember, your limiting reagent limits the number of moles of everything that reacts. So therefore, I can go, therefore, the number of moles of HCl that actually reacted is equal to the number of moles of NaOH, which is 0.001. The number of moles of HCl remaining is the total, which is 0.24, minus number of moles of NaOH, 0.001, which is whatever that is. Let's say that's C. Okay, so now I've got the number of moles of HCl remaining. What can I find, everyone? I've got N. Do I have the total volume of the solution, Ethan? Yes, no, Ethan? What's the total volume in the beaker right now, Ethan?
Wait. Give me 1 sec.
Britannia? Total volume in the beaker.
You have to add up all the.
Yeah, so what are the volumes?
.304 liters.
I don't think it's 304 because you don't have to worry about the 100 ml right now. Or you could do the 100 ml right now because the number of moles is fixed. So yeah, we could follow your way as well, Sid. So you go, all right, the number of moles remaining is C. The total volume in the beaker is 26.7 plus 83. What was it, 83? Yeah, 83.9 ml of HCl plus 97 ml of NaOH plus the new 100 ml that's added after. Therefore, we can go V. Is that equal to the amount you said, Sid?
Yeah.
Good. What is that amount?
Yeah, 0.304 liters.
Okay, good. So then we can find concentration. C of HCl is equal to N on V. It's equal to the C value we stored. It's not this C value we stored. Divided by 0.304. And what do we get as our concentration of HCl?
0.7861 ...
Okay, good. Store it as D. pH is what we're trying to find. pH is negative log 10 of D. What do we get?
Is this through HCl, the remaining HCl dissociating?
To completion, exactly. That's exactly how we're finding our answer. We're finding how much of that excess reagent is remaining, and since it's a strong acid, it ionizes to completion. Find pH. So what do we get?
Do you have to state the equation for that so that the markers know?
It's good to, right? Definitely good to. You can always write the HCl equation by itself. I haven't just for the sake of time, but you definitely can. You should. So what do you get?
I don't know if this is right, but 0.1044.
What did you get, Rithanya?
I got the same answer as well.
Sid, what did you get?
Yes, same answer.
Good. And it's actually possible to even get a negative number for pH, everyone. pH can be negative, okay? So I would agree that it makes logical sense, or qualitatively this could be the answer. So good. Round it up to the nearest decimal places. The question has two sig figs that I can see here. So we'll do it to 2 decimal places. So it'll be 0.10 as a pH. Good. Good question.
So pH can be negative, but can it be above 14?
No, can't be above 14. Or well, you can try it out. You can assume that you have a base that's of concentration 10 moles per liter. You can find its pOH. But yeah, if pH can be negative, if pH can be negative, then pH should be possible to be greater than 14. It should be, mathematically speaking. Yeah. You just will never see that in a question. Okay, but I have seen questions where the pH is 0 or close to negative. Okay. Good. Very good. All right. So, guys, key point in this question, this was not meant to be a challenging question. It took us a bit longer than normal, but hopefully it was because now you've got the steps on how to answer these questions. When you have an acid reacting with an actual base to form a product, it's always going to be an excess limiting reagent question. And so you always prepare yourself for that. And how much ever is left, you use that to either find pH if it's an acid. In this question, it was an acid, so the goal was to find hydrogen ion concentration and pH. If the excess reagent was sodium hydroxide, we would have found pOH first and then done 14 minus pOH to find pH. Questions are very repetitive. So questions 1, 3, 4, do this in your own time. These are all just harder variants of the question that I gave you. Okay? They love giving the question, but it's a very easy free mark question if you're good at calculations. Does anyone have any questions about approaching, the above pKa questions, which were very different, where they gave you buffers or a substance dissolving in water versus a true acid combining with a base? Any questions at all? Good. All right. Let's start talking about titration. This is the interesting part. All of Mod 6 is actually pretty interesting, but this is the highest yield exam part of Mod 6, titration. This and pKak, if you can nail those two topics, Mod 6 is a breeze. Okay, let's talk about titration. What do we all understand about it, going left to right? Ethan, what does titration mean to you? What have you heard about? What's your baseline understanding?
We've actually done an experiment. So we slowly it's kind of like dripping some solution in there, and then slowly turn to a color, and as soon as it turns to a color, we stop and we measure how much, like the volume of the solution we've used. Is that
Good.
what's
Good.
Yeah.
So, Ethan, you're describing a method which is very. Oh. My iPad randomly does this. I'm actually connected on two iPads, one for the writing and one for this. Sometimes on the iPad turns the mic on and then it echoes, so I apologize for that. But yeah, Ethan, you were describing the method of titration, which is very good. But before the method, you all need to understand what the goal of all those steps is. Right? Why are we adding a substance at a dropwise rate? And why are we looking for a color change? And why are we very carefully doing the entire experiment not to overshoot a color change as well? So, Sid, what's the goal of titration? You have to give me one line.
To find the concentration of an unknown solution.
There you go. That's it, right? So that's the first thing you need to say in any exam question that asks you anything about describing or defining titration. Titration is a form of analyzing solutions to determine the concentration, right? Now, for titration, we only look at liquids or solutions. Solutions have volume. Hence, titration is what we call volumetric analysis, analyzing by volumes. You would have learned in year 11, there's another form of analysis with mass. Actually, what do we call that? Analysis with mass. Come on, Akshita. I don't get to eat a watermelon if you don't get this. So, what is analysis by mass? What do we call that? Rithanya, help her out. Analysis by mass. Ashita, going back to you.
Mass spectrometry.
Spectroscopy. That's you didn't. I hope you didn't learn that in year 11. That's much more challenging concept. Gravimetric analysis, right? Gravimetric analysis is analyzing by mass. They'll tell you there's a 100-gram sample, 40 grams is carbon, 60 grams is hydrogen. What is the chemical formula? That is gravimetric analysis. Titration is a type of volumetric analysis. Okay, so again, we've got the goal. The goal is to find the concentration of an unknown solution. That is the first step. The second step is how, and the answer is through chemical reaction. Everyone, there are different kinds of titration. In Module 6, acid-base chemistry, you are only going to look at acid-base titrations. There are other reaction types we can use to determine the concentration of an unknown, right? But in acid-base chemistry, we're going to use neutralisation reactions to determine the concentration of an unknown. Good. The second thing I've highlighted here is that titration is a form of volumetric analysis. Determine the concentration of an unknown. So this is all things we've said, tick and tick. But I've said through stoichiometric reaction. I've also mentioned the word standard solution. Sid, what does the word stoichiometric reaction mean?
It means that you measure like the concentration like relative to the mole ratios of the reaction.
We're getting there. Stoichiometric just means there is no excess or no limiting reagent. Both reagents react exactly. Does that make sense? So in titration, the reason we're so cautious is because we don't want to overshoot in any of the reagents to cause an excess limiting reagent. As soon as we cause an excess of a reagent or a limiting amount of the other reagent, we've failed the titration. We need it to be an exact stoichiometric reaction because otherwise we cannot calculate the concentration of our unknown. Let me give you a very quick example to show you what I mean to find titration, right? So imagine that we have this reaction between A, B to form C. Now let's say C is a solution you know everything about. You know the exact concentration of not C. A is a solution you know everything about. You know its concentration. You know all of its volumes. And B is a solution that you don't know the concentration of. It's the solution you're trying to find the concentration of. Okay? Now what happens in titration is we get a fixed sample of B. So I want you to imagine we've got this little beaker. And in this beaker, we have our solution of B. It's a fixed volume. So let's say it's 25 ml. 25 times 10 to the power negative 3 liters. We're then going to react that with A. So A is going to be dropped down and reacted with B. Let's say we find out the exact amount of A that is required to react with B. So let's say that volume is a ticket, we'll say it's equal to X. Okay? Now we need this volume to be exactly stoichiometric, aka there should be no excess amount of A in this conical flask. What happens is, everyone, when we get the exact volume of A that is required to react with B, well, Brittany, we've got a C and a V. What can we find?
Moles.
Good. And since we've stoichiometrically reacted them, Britannia, we can use this stoichiometric ratio. So I've got the number of moles of A that was required. What would be the number of moles of B?
Would be the same thing.
Exactly, only because they stoichiometrically reacted. If I had an excess of A, if I had to double this volume, could I make this jump here, Britannia? Where the number of moles of A is equal to the number of moles of B?
Sorry, can you repeat the question?
If I added double the volume of A, could I still make the same conclusion that the number of moles of A is equal to the number of moles of B?
Yeah.
The answer is no, because it would not be stoichiometric then, right? If I add double the volume of A, I've added way too much A, right? There is no longer a stoichiometric reaction. A is the excess reagent. I'll then need to find the amount of A that reacted to then find the number of moles of B. Are you with me, Rithanya?
Yeah.
That's why it is so important for there to be a stoichiometric reaction. Without a stoichiometric reaction, you can't do this. You can't do this step here of applying the stoichiometric ratio. That is wrong. You can't apply it, right? In the previous question where there's an excess and limiting reagent, we couldn't just say the number of moles of HCl is equal to the number of moles of NaOH, because that would be completely wrong. There's a different amount of NaOH, there's a different amount of HCl, right? Only when the reaction is stoichiometric can you say the number of moles of one reagent and use that to correspondingly find the number of moles of the other reagent. So now, everyone, we've got the number of moles of B. I've got the volume of B. Can I find the concentration of B, Akshita?
Yep, I think.
Yeah, you can, right? Divided by 25, you get the concentration of B. That is titration in a nutshell. That is it. Titration is simply where we make sure we engage in a stoichiometric reaction between an acid and a base, and we use the formula here to find the concentration of that unknown. The most important thing, like I said, is for there to be a stoichiometric reaction. And that is why the technique matters so much in titration, because you have to be extremely accurate with the volumes you transfer and stop exactly when there is a complete reaction. Sid, question?
So with the unknown solution, how would you know like if the equation itself, like the do you know the chemical formula of B or?
Yes, you always know the chemical formula of A and B.
Okay.
If you don't know the chemical formula of B, you can't do the titration. So when I say unknown, the real unknown is a concentration. That's it. Okay, everything else is known. The chemical formula of the substance is known. The volume of that substance in in the beaker or the conical flask is known. Ethan, question?
Yeah. Do we need to also calculate a percentage error if we're doing this type of experiment as well?
You often will, and I'll show you how to calculate percentage error, and that could be a question in your assessment task, but I'll show you how to do that later. Okay?
Yeah. All right.
So far, all everyone needs to know, titration is a volumetric analysis for finding the concentration of an unknown, and it must be a stoichiometric reaction. Those three things are paramount. Any questions so far before I move on? Any other questions at all? Good. All right. So the goal of titration is to find the concentration of an unknown, but that's pending on the fact that there is an exact stoichiometric reaction. Now, there is a name for a point in time where you have the exact reaction between an acid and a base with no excess or limiting reagent. And that point is the equivalence point. So in titration, the way we can find the concentration of an unknown is by aiming for the equivalence point. And the equivalence point is the exact amount of solution A that is required to react with solution B. Okay, it's this volume here that I'm double circling here in the example above. Now, you also see this word standard solution. Does anyone know what standard solutions are? What is a standard? You might have come across it in year 11. I remember it used to be in the syllabus. Actually, do you want to tell me what a standard solution is?
It's just a solution that we know what's its concentration.
Accurately known concentration. So it's not just known concentration, it's a solution of accurately known concentration. Ruthania, did you want to add anything to that? Or is that what you were going to say as well when you raised your hand?
Yeah, that was all.
Good, good. All right. So now we know the terms. So let's talk about equivalence point. Equivalence point when the acid and base have exactly reacted with no excess or limiting reagent. Good. Now, here's my question to you. How do you know when an acid and base have completely reacted with no excess or limiting reagent?
Would you use an indicator?
Very good. Good job, Sid. So what you could use is in the conical flask, you can have one of the solutions. And in this other instrument we'll talk about later, you have your other solution. And you'll be adding, let's say, your acid, which is up here, to your base, which is down here. And you all know most neutralizations completely and exactly neutralize at pH 7. So we can add an indicator that is going to change from one color to another color at exactly pH 7. And that can tell us exactly when to stop the reaction. So we have a stoichiometric reaction and we reach our equivalence point. Okay, so again, equivalence point when acid and base have completely reacted. Now, this is the issue. There is no such thing as an indicator that exactly changes pH at 7. And so we have a name for the point when the indicator changes color. Does anyone know what that point is called? When the indicator changes color. Ethan?
Is it called the endpoint?
Exactly. Right? So endpoint is the point in the reaction where the indicator changes color. Now, Rithanya, do you think we want the endpoint and equivalence point to be similar, or do we want them to be very different? The endpoint and the equivalence point. So again, equivalence point when there's stoichiometric reaction, endpoint when the indicator changes color. Do you want them to be as close to each other as possible, or very different?
Close to each other?
Exactly, because you want the point when the indicator changes color to be the exact point that the reaction stoichiometrically reacts, so you stop the titration then and there. And that is how titration works in a nutshell. You add an acid to a base, and you add them until a stoichiometric reaction occurs, and you see a change in color, aka the endpoint, and that tells you when equivalence point occurs, because otherwise acids and bases are clear. And then you stop the reaction and you record the above data that we have, right? And we can use it to mathematically find the concentration of our unknown. Any questions so far? Good. So far you know the goal of titration, you know very vaguely what the neutralization reaction involves, why it needs to be stoichiometric, and a general calculation to get to your answer. Now we're going to talk about your different kinds of standard solutions. Now we're taking a step back. We're going to pause from titration, actually learn a bit of the prerequisite stuff, which is what are standard solutions and what are the different kinds? So actually, as mentioned, a standard solution is one of accurately known concentration. Now, there are two ways to standardize, or aka make a solution standard. The first way is what you learned in year 11. What was that first way? I'm going to use this diagram and I'll get one of you to explain it for me. So Rithanya, what's one way to make a standard solution?
You like weigh the correct mass of a salt, and then you would dissolve it in some point of water, and then you put it into a conical flask or a volumetric flask.
Good. Not conical, volumetric. Only volumetric. Okay. Good. Keep going.
And then you fill it up with more water until the graduation line, and then.
Good.
Oh.
There's a bit more detail to it, but that's essentially what you're doing, right? You're accurately weighing a mass. You're adding solution until you have a very accurate volume solution. And now if you have an accurate mass, you can find the number of moles from that mass. You can divide by the accurate volume you transferred, and then you'll get a concentration. When you make a standard solution from scratch, it's called a primary standard. Okay? Now, another way to accurately determine the concentration of a solution is through titration. Because remember, that's the goal of titration, to accurately determine concentration. Right? And so when you find the concentration of a solution through titration, so there's an already made up solution, and you find its concentration via titration, that is now called a secondary standard solution. So this is just about the terminology. Does that make sense? So essentially, titration is another way now to standardize a solution. Good. All right. Next lesson, what we're going to do is we'll recap the steps to make a primary standard, because that's also in the Year 12 syllabus. And then we'll talk about how we titrate or convert something into a secondary standard. For that, by next lesson, I'd like you all to read up to and do question 5, so 69. I'd like you to read up to page 69, do as many of the questions as you can, but ideally, I need you to do question 5. Okay? Good. Any questions so far? All right. Good. Good. Make sure you guys are taking some time up for yourself as well. I know Year 12 is, You know, it might be starting to get intense again. You might be getting your assessment tasks and depth studies, but take some time for yourself. Make sure you have systems in place so when you're not motivated, can't be bothered doing any work. For example, I used to bookmark the HSC countdown, and I used to have a website site blocker installed as an extension. So when I wanted to go on YouTube and procrastinate, it's kind of more barriers for me to do that. And it kind of helped me get on track as well. I'd also recommend creating like a vision or a manifestation of board. What I mean by that is literally breaking down every part of your life that you'd ideally like to have as your goal when you're in your 30s or 40s. Where would you want to live? What house do you want to live? Car do you want to drive? What job do you want to have? Just whatever motivates you. Have that on a vision board. I have mine on Notion. That kind of just reminds you why you're putting in the work now. Okay, and it will be important for those who are interested in medicine. It will be important for those who are interested in a high ATAR course. Okay. Any other questions before we finish for today? All right, good. All right, enjoy the rest of your day. Take a break from studying, go outside, chill, and have a great week. I'll see you on Saturday. Hey guys.
All right, bye.
Bye, Sid. See ya.
All right, thank you.
Bye, Ethan. See ya. Bye, Rithania. Bye, Chita.